Section: Introduction. In this section, we introduce test time scaling, a significant advancement in large language models, LLMs, exemplified by OpenAI's and DeepSeek's R1. This approach allows for extended chain-of-thought reasoning, enhancing the model's performance in complex math and coding challenges like AMI and Codeforces. The key driver behind this shift is large-scale reinforcement learning, RL, which fosters advanced reasoning behaviors such as self-verification and iterative refinement. However, the specific algorithms and methods for effective scalable RL training remain largely undisclosed in existing technical reports. We identify major challenges in large-scale RL training and present an open-source scalable RL system, complete with the algorithm, training code, and dataset, aimed at providing accessible solutions with industry-level results. Our experiments utilize the Qwen 2.5-32b model for RL. Initially, our Group Relative Policy Optimization (GRPO) run yielded only 30 points on AMI, which is notably lower than DeepSeek's RL score of 47 points. Our analysis indicates that the basic GRPO approach faces issues like entropy collapse, reward noise, and training instability. The broader community has faced similar difficulties in replicating DeepSeek's results, suggesting that essential training details may have been overlooked in the R1 paper, which are crucial for developing a robust, large-scale, and reproducible RL system. To address this gap, we release a state-of-the-art open-source system for large-scale LLM RL, achieving 50 points on AMI 2024 with the Qwen 2.5-32b model, surpassing the previous best of 47 points from DeepSeek R10 Qwen 32b while using only 50% of the training steps. We introduce the decoupled clip and dynamic sampling policy optimization (DAPO) algorithm, along with 4 key techniques to enhance RL performance in long chain-of-thought scenarios. These techniques include clip higher to promote diversity and prevent entropy collapse, dynamic sampling for improved training efficiency and stability, token-level policy gradient loss for long chain-of-thought scenarios, and overlong reward shaping to minimize reward noise and stabilize training. Our implementation is based on the VRL framework. By fully releasing our advanced RL system, including training code and data, we aim to provide valuable insights into large-scale LLM RL for the wider community. Next, we discuss proximal policy optimization (PPO), which uses a clipped surrogate objective for policy optimization. This method stabilizes training and enhances sample efficiency by keeping policy updates within a certain range of the previous policy. Specifically, PPO maximizes an objective that involves a question-answer pair from the data, a clipping range for the importance sampling ratio, and an advantage estimator at a given time step. We also cover Group Relative Policy Optimization (GRPO), which differs from PPO by removing the value function and estimating advantages in a group relative way. For a specific question-answer pair, the behavior policy samples a group of individual responses, and the advantage of a particular response is calculated by normalizing the group-level rewards. Like PPO, GRPO employs a clipped objective and includes a KL penalty term. However, GRPO computes the objective at the sample level, first calculating the mean loss within each generated sequence before averaging across different samples, which may affect the algorithm's performance. We note that the KL penalty term is typically used to manage the divergence between the online policy and a fixed reference policy. In the context of reinforcement learning from human feedback, RLHF, the aim is to align model behavior without straying too far from the initial model. However, during the training of long chain-of-thought reasoning models, the model distribution can diverge significantly, making this restriction unnecessary. Therefore, we propose to exclude the KL term from our algorithm. Lastly, we address the challenges of reward modeling, which often faces the issue of reward hacking. Instead, we directly use the final accuracy of a verifiable task as the outcome reward, calculated based on the ground truth answer and the predicted answer. This method has proven effective in activating the base model's reasoning capabilities across various domains, including automated theorem proving, computer programming, and mathematics competitions. Section Summary. In this section, we discuss the advancements in test time scaling for large language models, LLMs, through large-scale reinforcement learning, RL, which enhances reasoning capabilities in competitive tasks. We introduce our open-source RL system that addresses key challenges in training, achieving superior performance on AMI, and propose the decoupled clip and dynamic sampling policy optimization, DAPO, algorithm to improve efficiency and stability in long chain of thought scenarios. Section, DAPO. In this section, we propose the decoupled clip and dynamic sampling policy optimization, DAPO, algorithm. DAPO samples a set of outputs for each question paired with its answer and optimizes the policy based on a specific objective. We will introduce the key techniques related to DAPO. To tackle the issue of entropy collapse observed in our initial experiments with basic PPO or GRPO, we introduced the clip higher strategy. We noticed that as training progressed, the policy's entropy decreased rapidly, leading to similar sampled responses and limited exploration. The clip higher strategy involves adjusting the clipping of the importance sampling ratio to enhance stability in reinforcement learning. We found that the upper clipping limit restricts exploration, making it easier to increase the probability of common responses than to boost the likelihood of less common ones. For example, when considering two actions with different probabilities, the higher probability action faces less restriction in its potential updates. Our empirical findings support that the upper clipping threshold limits the probability increase for low probability tokens, which can reduce diversity in the system. By decoupling the clipping ranges, we allow more room for low probability tokens to increase, which enhances the policy's entropy and leads to more diverse samples. Next, we address the gradient decreasing problem in existing RL algorithms, particularly when some prompts achieve perfect accuracy. In such cases, the advantage for those prompts becomes zero, resulting in no gradients for policy updates and reduced sample efficiency. We propose a dynamic sampling approach where we oversample and filter out prompts with perfect or zero accuracy, ensuring that all prompts in the batch contribute effectively to gradients. This strategy does not hinder training efficiency, as the generation time is often dominated by longer samples, and we find that dynamic sampling leads to faster performance. Lastly, we introduce a token-level policy gradient loss to improve upon the original GRPO algorithm, which uses a sample-level loss calculation. This method assigns equal weight to all samples, which can disadvantage longer responses that contain more tokens. This can hinder the model's ability to learn from high-quality long samples and allow low-quality patterns to persist. Our token-level policy gradient loss allows longer sequences to have a greater impact on gradient updates, ensuring that individual token patterns are appropriately encouraged or discouraged, regardless of the response length. Section Summary. In this section, we introduce the decoupled clip and dynamic sampling policy optimization, DAPO, algorithm, which addresses issues like entropy collapse and gradient decreasing problems in reinforcement learning by implementing strategies such as clip higher for improved exploration and dynamic sampling to maintain effective gradients. Additionally, we propose a token-level policy gradient loss to enhance learning from longer responses, ensuring that all tokens contribute appropriately to the overall gradient update. Section: Hide and Seek, Overlong Reward Shaping. In this section, we discuss our findings on reward shaping in reinforcement learning, RL, training. We typically set a maximum length for generated outputs, truncating any that exceed this limit. However, we discovered that improperly shaping rewards for these truncated samples can introduce noise and disrupt training. By default, we penalize truncated samples, which can confuse the model, as valid reasoning may be unfairly punished for being too long. To address this, we implemented an overlong filtering strategy that masks the loss from truncated samples, leading to more stable training and improved performance. We also introduced a soft overlong punishment mechanism, which applies a penalty based on the length of the response. If a response exceeds the maximum length, the penalty increases with the length, encouraging the model to avoid overly long outputs. For our dataset, we sourced it from the AOPS website and competition pages, using web scraping and manual annotation. The answers varied in format, making it hard to create parsing rules. To ensure accurate reward signals, we transformed answers into integers, simplifying parsing. For instance, if an answer was originally in a complex format, we adjusted it to a straightforward integer. This process resulted in the DAPO Math 17K dataset, containing 17,000 prompts paired with integer answers. In our training, we focused on mathematical tasks, using the Virl framework and naive GRPO as our baseline. We set hyperparameters with the Atom W optimizer and a constant learning rate, along with specific settings for batch sizes and token limits. Our overlong reward shaping set the maximum length at 16,384 tokens, with an additional cache for penalties, totaling 20,480 tokens for generation. We also adjusted parameters for the clip higher mechanism to balance exploration and exploitation. Our experiments on AMY 2024 showed that DAPO effectively trained the Qwen 32B base model, outperforming DeepSeek's results with fewer training steps. We noted a significant accuracy increase, demonstrating the effectiveness of our training techniques. While token level loss didn't greatly improve performance, it did enhance training stability. Dynamic sampling required more data but did not significantly extend training time, and in fact, reduced convergence time. We recognize that RL with large language models is complex, with interdependent subsystems. Changes in one area can lead to unexpected outcomes, making it crucial to monitor intermediate results. The length of generated responses is a key metric for training stability, allowing for more complex reasoning. However, response length can fluctuate during training, and we use it alongside validation accuracy to gauge experiment health. We also track the dynamics of reward during training, which generally remains stable. However, we found that the final reward often correlates poorly with validation accuracy, indicating potential overfitting. We monitor the entropy of the actor model and generation probability to assess exploration capabilities. Maintaining an appropriate entropy range is vital, as too low can hinder exploration, while too high can lead to poor output quality. Our clip higher strategy helped manage entropy collapse, and we observed that a gradual increase in entropy supports model performance improvement. Section Summary. In this section, we address the challenges of reward shaping and reinforcement learning, RL, when dealing with truncated samples, proposing an overlong filtering strategy and a soft overlong punishment mechanism to stabilize training and improve performance. We also detail our dataset transformation process, training dynamics, and the importance of monitoring key metrics to ensure effective model training and performance evaluation. Section: Case Study. In this section, we examine a case study from our reinforcement learning training process, where we notice a fascinating trend. The reasoning patterns of our actor model change over time. Our algorithm not only strengthens existing reasoning strategies that help solve problems correctly but also develops new reasoning approaches that were not present at the start. This highlights the flexibility and exploratory nature of reinforcement learning algorithms and provides fresh insights into how our model learns. For instance, in the initial phases of training, we rarely observed the model checking or reflecting on its previous reasoning steps. However, as training continues, we see the model starting to reflect and backtrack, as illustrated in our findings. This observation encourages us to further investigate how reasoning abilities emerge during reinforcement learning, which we plan to explore in future research.